Good evening, everyone. Welcome to the Astro Imaging channel, back again on this lovely Sunday night. My name is Molly, and tonight we have with us Dr. John Hayes, who's going to talk about the physics of dew prevention. So that should be really interesting. Before we get to John, I have a couple of announcements. So first, I want to remind everybody, we are now streaming in 1080p, which is very exciting. That includes our speakers' screens, which is a big deal. So make sure you select, hit the settings icon and select 1080p as your resolution if you want to see that, and if your internet connection supports it. Let me share my screen. Oop, that's not the right button. Share my screen real quick. Just look at our calendar. All right, so upcoming, and these times are showing in Pacific time right now for some reason. So next week we have Rod Pommier back with us. He was on a few months ago, 1 or 2 months ago, and through a series of technical difficulties was unable to actually give his presentation. So we're going to have him back on the 21st at our next show to actually give his talk on correct identification of Lynds dark nebulae and the interesting problem with that. On the 5th of October, we have Craig Stocks coming on. I need to circle back with him on what the title of his talk is, but he's going to talk about systems and webcams for observatories, looks like is the general topic. And then we have John Talbot back with us on October 19th, talking about a scientific topic of discovery of nebulae around cataclysmic variables. That should be a lot of fun. And then we got a couple open slots. I'm working on another talk on safety systems for observatories. So I'm going to get that on the schedule here soon. And we do have some open slots. So if you're interested in coming on and giving a presentation, I would like to have more on a kind of back to basics topics. So like how to get started in processing, things about, beginners topics about gear, things like that. I'd like to get some more of those topics on here. So this would be a good opportunity for a lot of folks, I think, to come on and speak on those topics. We were having a discussion. I'm going to stop sharing my screen here. We were having a discussion before the show about we could really use a talk on a survey of astronomy target tools. So tools that can help you find targets, figure out where they are in the sky, discover new things to image or to go look at, things like that. Things like Telescopius, Gary Im's Compendium, Sky Tools, things like that, kind of to give a survey of what tools are out there and what the pluses and minuses of those tools are. So if you're interested in giving that talk or any other talk, go to our website, theastroimagingchannel.org, hit the contact us button. One of us will get back with you soonish, and we can work on getting that scheduled. So let's see, was there anything else? Yeah, so as a reminder, we are doing 2 times a month now, the first and third Sundays of the month. And so we're not streaming every Sunday anymore. So keep an eye on our calendar and on the Facebook page to see when our next show is. All right, with that, I want to go ahead and introduce our speaker. So Dr. John Hayes is a retired optical engineer, entrepreneur, and professor with a BS in physics and astronomy, master's in optics, and a PhD in optics from University of Arizona. He has numerous publications and patents in optics and atomic force microscopy. His astronomy interest started in elementary school, and now he has a rig down at OBSTech in Chile, which I'm very jealous about someday. He's earned 23 Image of the Days on Astrobin, and he has 2 NASA APODs as well. He's also an active pilot and flight instructor. We've had him on the show several times, and we're happy to have him back tonight to talk about the physics of dew prevention. So, John, take it away.
Well, thank you, Molly. Let me see. Let's get our screen shared here. I'm going to press that button first, and we're going to see here. Oh, gosh. Select a tab here. Stand by just 1 second. Let's.
I guess we did forget to run through that. Click on select your entire screen on that.
Yeah, I'm going to do that. Yeah. So we're going to do this, and we should see. We should see my presentation there somewhere. Where's the screen? Oh, entire screen. There we go.
And then you have to hit share.
Yeah. And entire screen and share that. There we go. All right. And now we just need to find the presentation, which went off, hiding off to the side here. There we go. And you should see in just 1 second here. We should see that over the whole screen. Do we see that?
Yes, and then down toward the bottom, there's a button that says hide next to where it says stop sharing.
Yes. Okay.
Just hit
And
that hide
we'll hide
button.
that. There we go.
Perfect.
Okay.
Hit
And
Command Tab to switch back to your presentation.
Command Tab. Oh,
There you go.
there we go. All right. Okay. Thank you, Molly, for that help.
Yeah.
Well, thanks for inviting me back. This is always a lot of fun to come talk to everyone on the Astro Imaging channel. And this is a subject that I really enjoy a lot. I think if I wasn't in optics, I would be doing thermodynamics or heat exchange. I really love this kind of stuff. And this is a new and improved version of the same talk that I gave at NEAC this year. And when I gave that talk, people were filtering in, and I complimented them on the fact that they were showing up for a talk with the word physics in the title. And one of the guys screamed out and shouted out, he said, "That's why we're here." So I hope you're my kind of people here and you like physics, because we're going to talk a little bit about some physics tonight and try to understand more about the best ways to prevent dew. And who hasn't run into dew? You know, I've imaged pretty seriously from 3 locations: Central Oregon, Northern New Mexico, and Central Chile. And all 3 of these are high desert. And all 3 of these can exhibit significant dew. You know, dew is pretty common, even in the high desert. In Chile, I had a number of people tell me, "Oh, it's perfectly dry down there." This was a photo from my very first visit to my CDK-20 down there, and there was water. Water had clearly run down the side of the telescope. And I've been down there when everything is just soaked, and it's a very, very dry area. But it's in fact how the plants and animals live down there. They live off of the dew. So dew is definitely a consideration even in this dry area of Chile. Now, it seems like every time I bring up the subject of dew prevention, it starts a food fight. And this is I think there's a good reason for this. Everybody has their own idea of what works. And there are a lot of ways, a lot of methods that work pretty well to prevent dew. And so tonight, really what we're going to try and talk about is there a better way to do this? So I don't want to talk about this stuff and imply that, you know, different methods don't work. They do, but there are better ways than others to try to prevent dew. And we'll go into that. So we're going to start out with kind of very gently talking about what causes dew and what causes frost. And we're going to talk about the thermodynamics and heat transfer. What's the difference between those? And then how to most effectively prevent dew and how to minimize the amount of heat and the impact on image quality. And these are all considerations when we talk about dew. We have to start out with some basics. You know, what is relative humidity? Well, relative humidity is officially defined as the ratio of water vapor pressure in a gas to a saturated water vapor pressure over liquid water surface at the same temperature. But in simple terms, relative humidity describes the amount of water that can be held as a vapor in air as a percentage of the air, that air volume's maximum water holding capacity. And it's a function of temperature. The dew point is the temperature where the relative humidity is 100%. And water will condense on any surface that has a temperature at or below the dew point in any massive volume of air. If the temperature of the air goes down to at or below the dew point, that's when fog forms. And so temperature within an air mass can vary by about 3 degrees centigrade, and fog can form anywhere within about that 3-degree limit of the dew point. So if you know what the dew point is, and let's just say it were, for example, 5 degrees C, you have to be wary that within about 8 degrees, you can begin to have fog forming. Okay, so that dew point temperature isn't a precise number where dew forms on one side of it and not the other side. You'll begin to develop dew within about 3 degrees C of that dew point. And here I've plotted how the dew point varies with air temperature. And the dew point is calculated by this kind of crazy looking complicated formula here that I've added to the chart. And as you can see, I've actually plotted the relative humidity all the way up to 100%, that sort of lavender line on the top. So if we were to pick a temperature of, say, 10 degrees C and that the humidity is 100%, well, the dew point's at 10 degrees. But as the temperature gets drier, down to, say, 10%, the dew point falls. And so if we were to look at 10 degrees C for the air temperature, at a relative humidity of 10%, the dew point's down at -20. So you have to get pretty cold when it's dry in order for dew to form. And by the way, that's a big consideration if you go to the Arctic. And most of us don't image in the Arctic. But down in the Arctic, it's typically very dry, but it's also very cold. And so you can get dew and frost forming even when it's very dry. And we can plot this data in a more useful way, and that's to plot the temperature dew point spread. So in other words, at 100% humidity across the top, the spread between the outside air temperature and the dew point is 0 degrees. And if we kind of pick that 3-degree range of where dew can form, you can see that down to about that upper green line, which is what, 80%, let me look here, that's 90, 70, 80% or so, or 70%, excuse me, 70% dew. No, that's 190, 80%, excuse me. That's where you'll start to get, you could possibly get fog. Okay, so the more dry it is, the larger the dew point spread is. And what about frost? I mentioned that a little bit. Frost is actually not frozen dew. Frost is when water vapor transitions directly from a gas into a solid without passing through the liquid stage, and it's called deposition. The frost point occurs slightly above the dew point. It's sort of in the range of 0 to 3 degrees C. And frost occurs typically below about 3 degrees C. Now, it turns out, if you look at the frost point deviation, and that's the separation between when the dew point and the frost point, it turns out the drier it is, the larger that deviation is. Now here I only plotted it up to about 55%. So it's less than a degree. So you can see if it's pretty close to freezing, you're going to get frost. And that's an intuitive result. But I just want to emphasize that frost is not the same thing as frozen dew. Now, at lower relative humidity values, you get a bigger deviation. And again, that's really more applicable to the Arctic, where the relative humidity might only be, say, 10% or so. And then you could have frost forming even above freezing. Fog is driven by the temperature dew point spread and how air flows around your local topography. So where you set up can make a big difference. Those of us in remote observatories don't get that luxury of setting up in different places. But if you image, say, using a tripod or your favorite location, where you set up can make a big difference as to whether or not you get fog. And there's different kinds of fog. And, I'll just mention a few of them. Advection fog is when cold air flows from, cold moist air flows from over water over land. There's upslope fog when air rises and adiabatically cools as it goes up the slope, and you can get fog from that. Radiation fog happens on a really clear night when radiation to the sky can cool the air. And there's probably, I want to say there's 3 or 4 other kinds of fog, but this isn't a weather course. So, I'm not really trying to educate everybody on all the different kinds of fog. But there are different kinds of fog that can affect your imaging. But the important thing to remember is if you're able to see the stars, and that means there's no fog, the dew point has to be below the air temperature, okay, in general. And if your telescope components are at the same temperature as the surrounding air, you won't get any dew on them. So just remember that. If you can see the stars and you keep everything at the air temperature, you're pretty safe against having dew form. But of course, this happens all the time. You end up with your optics getting colder than the air. And so to understand how that happens, we need to look at just a little bit of physics. And to do that, we need to understand the physics of heat. Heat is thermodynamic energy. and energy is conserved. That's the first law of thermodynamics. Temperature difference drives heat flow from one system to another, and heat always flows from a high temperature to a lower temperature. And that's the second law of thermodynamics. Thermodynamics deals with the amount of heat that's transferred, and it generally deals with transitions between equilibrium states. Heat transfer, on the other hand, deals with the rate of heat transfer, and it deals with non-equilibrium states. So when we talk about the field of heat transfer, we're talking about how heat transfers in non-equilibrium states. And by the way, heat transfer is a really big deal for people who build buildings and that sort of thing. And we'll mention a little bit of that as we go along here. And there's three mechanisms of heat exchange. And this is where I see things fall apart when I try to discuss this stuff online. We all know about conduction. If you pick up a hot coffee cup, heat flows through the liquid into the cup and into your hands. And it can flow through liquids and gas as well. So it's the most common way that we think of heat transferring. So it's conducting through material. The one that we often forget about is radiation, heat flow by radiation. And that's the heat flow that you feel when you're in front of a fireplace, put your hands up, and you can feel your hands being heated. It's what you feel when you're out in the sun and the sun is heating you. And the third method of mechanism of heat exchange is convection. Heat flow through moving gases, liquids, or gas. It's how you can cool something with a fan. Those are the three mechanisms of heat exchange. So when we talk about our telescope, the question is, what causes what? Conduction and convection from the surrounding air work to keep your telescope at the ambient air temperature. Okay, so the telescope is surrounded by this air that is below the dew point, and through conduction and convection, it's trying to keep the telescope at the ambient temperature. It's radiation that's working against us. And radiative heat exchange goes by the Stefan-Boltzmann law, which describes the rate of heat flow emitted or absorbed by an ideal black body at a given absolute temperature. And if we say that Q represents the energy that's being transferred in heat, the rate of change, dQ dt, is equal to the Stefan-Boltzmann constant times the area. Remember that. It's the area times the temperature to the fourth power. That fourth power really drives things pretty strongly. Whenever you see a power that's a power of 2, that's important. When you see a power of 4, that's really important. So just keep in mind that radiative heat exchange is driven by this power of 4 value. And I mentioned a black body. What is a black body? A black body is any body that absorbs all incident radiant energy. Okay. And when I say all incident radiant energy, that means at all wavelengths. Okay. It means at all angles of incidence. It means there's no reflection. Everything that strikes a black body has to go in. Now, in equilibrium, that also means the black body has to radiate an equal amount of energy. So energy going in equals energy coming out for the black body to be in equilibrium. It turns out that, when we talk about all radiation at all wavelengths, that means a wavelength of infinity. That implies that a black body is a theoretical construct. It's not something that's real. So instead, we talk about things called gray bodies. And a gray body is a body that's close to a black body, and it can be really close. And in that case, the absorptivity, what it absorbs, is equal to the emissivity, but it's less than 1.0. It's less than 100%. So a gray body can be very, very close to a black body, and it's possible to have gray bodies in a laboratory where the absorptivity and emissivity is equal to like 0.999. I mean, it's very, very high. So it's possible to get close to a black body, but remember that a black body is an idealized concept. And this is a really remarkable thing when we talk about how does a black body radiate. And this was kind of a 100-year problem. This was a big deal. And Max Planck came along and solved this problem, because up until the early 1900s, when physicists tried to understand how a black body radiates, they ran into this thing that they called the ultraviolet catastrophe. What that meant was when they started adding up all the light that came out, they couldn't quite resolve it. They couldn't figure out an equation that accurately described how light was emitted from a black body. And in fact, in the short wavelengths, the blue end of the spectrum, the ultraviolet end of the spectrum, it showed that the power would go to infinity, which was clearly wrong. And in the early part of the century, Max Planck solved this problem by assuming that energy was quantized. So he received the Nobel Prize for this because he was one of the earliest guys who came up with really clear evidence that energy didn't come in continuous amounts. It was quantized. It came in little discrete packets. And you can still read about his derivation. He used probability theory to determine how a black body radiates. And this shows the emissivity of a black body as a function of temperature and wavelength. And you can you can differentiate this expression with respect to the temperature and look for the peak and determine the maximum wavelength emitted by a black body as a function of temperature. And I've put that relationship right down at the bottom there. It shows that it's just in microns, the wavelength that's emitted is 2,897.8 divided by the temperature in Kelvin. And that's gives you the peak wavelength that's emitted. And it turns out that that's how we determine colors of stars and the colors of hot objects. So just for fun, we can say, look at room temperature, which is around 20 degrees C. And I know those of you who live in a Celsius world, that's maybe a little cool for room temperature, but it's close. Room temperature is 293 degrees Kelvin. Well, that gives you a maximum emission at about 9.9, roughly call it 10 microns. If we go to minus 20 degrees C, say we're in the Arctic, that's more like 11.5 microns. So, the range we're talking about here is in the infrared for most common temperatures. And it ranges from kind of 9 microns to 12 microns. And it's, the range that you feel, the radiation you feel coming from a fireplace. And I should have calculated that. But again, that's in the infrared. Glass, by the way, optical glass, we look right through optical glass in the visible. But optical glass is opaque at these wavelengths. It has an emissivity of about 92%, and it's opaque. So when we're talking about heat exchange to optical glass looks like a pretty good absorber. It's black. And by the way, this is also how we determine the color of stars, and it's how hot objects glow. So this determines the color of glowing hot objects, and it describes the color of stars. Stars, by the way, make up a pretty good black body. So now we have to talk about the temperature of the sky. And the temperature of the sky, if we go to space and we look out into space, and we did this with a satellite called the Cosmic Background Explorer, was the name of the satellite. And we measure the background radiation. It's almost a perfect fit to a black body spectrum. And this shows the fit, and it shows the data, this lower plot. And it shows that the spectrum for deep space is like 2.728 Kelvin. It's really cold. It's really cold. And it's very uniform. It's uniform to 1 part in 25,000. But the Cosmic Ray Explorer satellite was very, very sensitive, and they could actually look at small variations in the background radiation from the sky. And this upper plot kind of shows some of that non-uniformity. But remember, that non-uniformity is extraordinarily tiny. And so the overall message here is that the sky background of space is very cold. And by the way, it's one of the reasons that James Webb Space Telescope operates at 30 degrees Kelvin, because it's radiating to this 2.7 degree black body radiation in the sky. And by the way, that gives us a clue to the size of the universe, because if we look at distant objects, they're receding, they're redshifted. And the idea is that this is redshifted radiation from the beginning of the universe that's redshifted all the way down to 2.728 degrees. So it's just so far away. It's moving away from us so fast, it's redshifted down to that temperature. So then the question becomes, well, how cold does the sky really appear to us? If we're in space, it's 2.7 degrees. But remember, we look at the sky through a warm atmosphere that thins with altitude. And water vapor absorbs radiation at long wavelengths. And so it plays a big role in the temperature that we observe. So the sky in general is colder when it's dry than when it's wet. And this turns out to be a really important question for people designing buildings, for example, in desert areas. And one of the sort of the holy grails of designing buildings for desert areas is, how do you figure out how to use that cold sky to cool buildings during the night so that they're comfortable all the way through the daytime? And so there have been a lot of studies, and most of the studies are not optics related or astronomy related. They're mostly related to cooling buildings. And this is a plot showing various studies of sky temperature. And the one that's most widely accepted that I can tell, and I've read lots of papers on this, is the study done in 1984 by Martin and Berdahl. And they surveyed lots of different sites. This is for data looking straight up. And they came up with a sky model that's shown here in blue. And that's typically, for a lot of remote observatories, that's typically the sky temperature that they'll show on their sky temperature weather, their weather system. Chen et al. At the University of Nebraska did another study that was similar, and they got a similar result. Walton is a little bit different, but the one that's really different is Swinbank, and that's the green line on top. And those guys used a completely different method. And so not surprisingly, they kind of came up with a different result. And I haven't seen very many people that use that method. Maybe some do. And I'm not a full expert in this area, so I won't claim that that's not a good model, but it's a different model. And most people use Martin and Berdahl. And so it's a good measurement, and we're going to use that in our discussion going forward. And if you were to plot the Martin and Berdahl model, sky model, showing the temperature of the sky and actually include the relative humidities, you can see how it varies. And so if we were to pick, say an ambient air temperature of 10 degrees, that's kind of a summer night up in Chile. And maybe for a lot of us in the Northern Hemisphere, in cooler areas, not full on desert. But, you can see that the model varies kind of between -8 and minus 22 or so degrees C for the sky temperature. So, the general thing here is the sky's pretty cold. And if we plot that a different way, if we just say, how much colder is the sky than the ambient air temperature? Well, and you can see it here more easily. And I've kind of created a green area there to show where most of us in the Northern Hemisphere operate, kind of -5 if you're hardy and up in Minnesota imaging in the wintertime. To those of us in the Northern hemispheres where it's not full on desert, or the Southeast, where it's generally kind of in the low 20s or so. And you can see, it varies from kind of -10 to -30 degrees below the ambient air temperature, depending on the humidity. And this really emphasizes the importance of humidity in this whole question. So this, obviously this relates to the radiative heat exchange of your telescope to the sky. And we're going to start out and we're going to consider just Schmidt-Cassegrain telescopes. And we're going to do that in the beginning here, first because I love Schmidt-Cassegrain telescopes, and I imaged with them for a long time. But they're just a great example for this because they have a glass element right in the front, and it makes it really easy to have that glass element exposed to the sky. And I want you to remember, when we talk about radiative heat exchange, we're talking about a peak wavelength that's somewhere, 11 or 9 to 12 microns. It's happening in the invisible. We can't see this. And remember, we have an area, and the radiative heat exchange depends on the area, and we have some temperature. And here I've just said, let's assume it's 5 degrees. And I'll come back to that in a second, but I also want to mention, this is one reason why when you go under the cold night sky, even in the summertime on a beautiful summer night, you get cold pretty fast. Your body is radiating to this cold night sky, and it's sucking heat out of you. And you know, I for years I'd never really thought about this, but you know, you go down when I go down to Chile, I tell everybody, be sure you bring a big coat. And they'll say, well, it's summertime. And I said, it doesn't matter. You will be freezing cold in no time at all down there because you're not moving around very fast. And the night sky is very clear, it's very dry, and it's sucking heat out of you like there's no tomorrow. You're exposed to a giant heat sink that's minus 20 to minus 30 degrees Celsius. And it's just sucking heat out of you, regardless of what the air temperature is. And by the way, this is why your house feels colder in the wintertime. The windows are sucking radiative heat out of you. Even if they're triple pane windows, if you close the curtains, your house will feel a lot warmer. This is a very important aspect in our everyday lives that we just don't even think about. So a big question is, we take that C14 that I like and we do a little calculus, and I spared you guys all the calculus here. And the result almost looks obvious, but you need a little bit of math to show this. But this shows the power loss to a hemispherical sky. And it turns out a C14 at 5 degrees C loses 9.8 watts to a minus 20 degrees sky. That's a lot of power. And if I actually calculate this over all the air temperatures, and this turns out to be kind of a complicated calculation, and there's a little bit of a story behind this whole calculation. And I've worked on this for a long time, and I think these results are actually the right answer. But this is just assuming you take that C14 plate and you suspend it under a hemispherical sky, and we don't have a telescope attached to the bottom because that makes it really complicated, because we have to worry about where's the heat come from, where's it go to. So let's just assume we just take that piece of glass and we just support it very carefully, just float it there. Just how cold is it going to get? Well, look at this. This shows the actual power. First, it shows the power loss, and we'll come back to how cold does it get in a minute. And you can see, let's just pick our 10 degrees. We're losing it somewhere between 8 and over 12 watts of power to the sky from this 14-inch corrector plate, depending on the humidity. We lose less power when it's more humid, and more power when it's less humid. Okay, and this again is assuming the Martin and Bardell's sky model, and it's assuming that the glass is held at the air temperature of the sky here. So this is when you just first take it out and set it down. How much power is getting transmitted? Well, that's a fair amount of power. You know, that's like a refrigerator light bulb. You know, this is all happening in the IR where you can't see it. So this is a lot of power. And whenever I've had my discussions online, people tend to forget about this aspect of heat exchange. And I don't think a lot of people really appreciate just how much power is being transferred to the sky from the glass elements. Now, of course, remember, it is related to the area of the piece of glass. So a smaller telescope is radiating less power, but a bigger one's radiating even more. And so when we talk about heat flow to the sky, it's kind of a busy slide. So let me just run through it real quickly. The effect, the cold sky is very cold, typically 10 to 30 below, as we've said. It acts like a big heat sink, driving the cooling process. And at higher temperatures, that T to the fourth radiation term grows much faster than the linear conduction convective terms, which causes a larger temperature drop when the sky is really cold. Obviously, I keep saying it over and over, higher humidity increases the temperature, which reduces cooling, while dry conditions enhance the radiative cooling. And it's nonlinear. Again, that T to the fourth radiation dependence creates this curved relationship that you see in the plots. And the radiation energy loss to the sky can be enough to cause frost even when the air temperature is above freezing. So, you know, that's a really important reason that you can get frost even when it's not that cold out. Well, this was the calculation that I spent a really long time doing, not the last one. This is the one, is determining, you know, just how much of a temperature drop do you get for a 14-inch corrector plate under the conditions I described. And I think that these numbers are pretty close to right. So if we were to look at, say, my favorite, which is 10 degrees C, you can see the drop is somewhere between a little over kind of 3.2 degrees C to almost 5 degrees, depending on the relative humidity. When it's hotter out, up to 30 degrees, that variation is a lot. And it can be really low for going up to 90% humidity, you can hardly get any drop. But at 90% humidity, we're probably getting pretty close to having fog anyway. When it's really, really cold, that temperature drop can get all the way down to -5.5 degree drop on that corrector plate. So that's a fairly significant drop. And even at the less extreme temperatures, even at 0, it's a pretty big drop, 3.5 to 4.5 degrees. So if we were to plot that again in a different way, take that 14-inch corrector plate and plot that temperature dew point spread for that thing, we can actually see when dew will appear. And again, we got to remember that kind of 3-degree uncertainty range here. And this shows that when the relative humidity is greater than about 65%, you stand a pretty good chance of dropping the temperature of that corrector plate right into the dew zone. So 65% is where you need to really have your antenna up. And as it gets more and more humid, 70%, you're almost for sure going to start getting dew at almost any temperature. 80%, you are getting dew. So, this kind of is a theoretical calculation, but it matches my experience out in these dewy areas. I also want to mention, that warm air can hold a lot more water than cool air. And I pulled up this graphic which shows oxygen molecules. In reality, we all know that air is 78% nitrogen, 21% oxygen. But in a hot air mass, there's kind of, the way I like to think of it, there's more space for water molecules in there, H2O. And this is one reason why dew in the southeast US during the summer is much worse than dew in the desert Southwest, because when it's really hot and humid, you can end up with everything really getting soaked. A lot of water can come out of the air when you hit the dew point. And I love to ask this question, and those of you who are pilots will know the answer to this almost immediately, so you can't tell everybody else. But the question is, and I want you to think about it, is humid air with water in the air, is that more or less dense than dry air? And that's a great thing to think about a little bit. So think about that. As a pilots, we have to know that. But for those of you who may not have done any pilot training, that's a good one to think about. How about bringing your scope inside? If it's wintertime and it's really cold, if you bring it inside, you're going to have the scope is going to be well below the dew point, and it's going to get soaked. So you don't want to bring a telescope inside directly from imaging outside when it's really cold. Store it outside where it can be warm gradually, and stay above the dew point. So let's flip over. We're about halfway through. We can talk about how do we prevent dew, and this is some fun stuff. We can look at some ways of some things that work, and we'll start off with one of my favorites, which is a passive dew shield. A dew shield limits the solid angle view of the sky from the front element. Okay, so it's best if you use just a standard shield, if it's non-conducting or it's insulated, and it's reflective to keep the temperature at the ambient temperature. You don't want it to get cooled by radiation as well. And just to be sure we're all on the same page, I'm defining the aspect ratio of a dew shield to be the ratio of the length of the dew shield to its diameter. And that's what determines the solid angle of the view that the corrector plate gets of the sky. So really what we're doing here is we're just limiting that view of the sky, and we can then calculate, well, how effective is it? And again, a little bit of calculus, it just turns out to go as the sine squared of the angle. And if I plot that as a function of aspect ratio, and most commercial dew shields have an aspect ratio of about 1.5. Well, guess what? At 1.5, only 10% of the power gets transmitted. So we can cut down all of that power loss. That 10 watts goes down to 1 watt of exchange. So a dew shield is remarkably effective at cutting down the amount of radiative heat exchange that you get with the sky. Obviously, as the dew shield gets more stubby, if it's an aspect ratio of 1, you get to twice the amount of power, 20%. So you're only getting down 1/5 the power. If you go twice as long, you get down to almost half, down to about almost 5%. But of course, as the dew shield gets longer, it becomes more susceptible to wind. So we really generally want to keep our dew shield as short as we possibly can, particularly for remote applications where we can't control the wind. And down in Deep Sky West, when I had my remote system, I generally would run it somewhere around 0.7, I believe it was. I don't think I ever went to a half, but it's around 0.7 to reduce the sail area of the dew shield with respect to the wind. Well, how about if we heat the shield? We could put multiple straps to achieve heating, uniform heating, and we could set the temperature of the shield to radiate the exact same amount of power lost to the sky at the center of the glass. And in this case, we want a metal shield to conduct the heat. And we want it black on the inside to really radiate as much as we can. Remember, we want that emissivity as high as possible, which says the inside should be black, particularly in the IR. Well, then the question is how hot do we need to run the dew shield? Well, we can easily compute this. We have to make a couple of little assumptions, but the goal is to just simply calculate at what point does power lost to the sky equal power gained from the dew shield. And if we assume a uniform dew shield, we assume the dew shield emissivity is 1. And we got to do that for mathematical convenience. It gets complicated if it's 0.9. So this won't be the perfect answer, but it'll be close. And we're going to assume the Martin and Berdahl sky model. And it turns out the expression that we get looks like this. And there's some kind of funny constants in there, which you can track through. And if we plot that, we can see how much temperature change we need to perfectly replace the amount of power lost to the sky. And it turns out to be about 2.5 degrees C for a C14. That's only 0.8 watts for a C14. And look at that. For various air temperatures from -10 to 20 degrees C, the data is pretty well clustered together for a dew shield aspect ratio of 1.5. And remember, I said it's not perfect. I assumed, we have to assume an emissivity of 1 to get it to work, to simplify the math and get a nice result. Well, should be a little bit warmer. So maybe we set it a half a degree warmer to 3 degrees, and that should work beautifully. And in fact, that's what I used to do down in Deep Sky West. And I used to run it a little bit with a little bit shorter dew shield, again, for the wind. Well, why do we care about this heat? Why do we want to run it so cold? Well, this is from back in my interferometer days, and we had developed the ability to make movies from our interferometers. And there was a coffee cup sitting there that had probably been sitting there for about 4 hours. So it really wasn't very hot. It was just a little bit above ambient temperature. And I put it into the test beam and made this movie. And I've used this movie so many times. I wish I'd made it longer. This was only like a 5-second clip, but I've used it. And it's a great illustration of what happens to the optical phase when there's a heat plume happening in the beam path. And by the way, this is what it looks like if we just took a 5 foot or so, maybe not quite 2 meter air path, and looked at just regular. This was just in the lab. This was just a 4-inch or 6-inch diameter, 6-inch diameter test beam, and you can see what's happening to the optical phase. And you got to remember that the optical wavefront accuracy is what determines your image quality. Rayleigh tells us that the system is diffraction limited if the peak to valley wavefront error is a quarter wave or less. And air turbulence can introduce many waves of wavefront error. Now, obviously, seeing does that. So, we can't control that. But what we really want to do is we want to minimize the excess added heat to our system to minimize that air turbulence, to maximize our image quality, minimize image degradation, I say here, but we want the best possible image. And the more heat we add, the more turbulence we have, and it's basically creating really poor local seeing conditions. So we want to minimize that amount of heat. So remember this, the ultimate goal is really to hold the optics at the same temperature as the surrounding air. And when that happens, there's no temperature difference, there's no heat exchange, there's no turbulence, and there's no image degradation other than from the high altitude seeing. And any heat we add has to go somewhere, and it will ultimately cause convection that can enter the light path. So we want to minimize that amount of heat. So let's look at some of these other ways to do it. First, I want to mention we can use convection to prevent dew. And I mention this because my telescope uses this method. And convective heat exchange is given by this expression, where the rate of heat exchange is given by some constant, the coefficient of convective heat exchange. Again, there's that area, the area times the difference of the temperature of the local surface to the temperature far away from the surface. And this is called natural convection. And by the way, this is old stuff. Newton came up with this. I think Newton touched everything, but this is a formula that Newton derived. So we can use that in the way of using fans. Fans can increase that coefficient of convective heat exchange, and we can increase it by about a factor of 4. And what we're doing there is we're blowing ambient air over the surface to replace the heat loss due to radiative exchange with the air with convective heat exchange with the local air to hold that surface at the air temperature. And in my telescope, we'll come back to this, it uses fans to do this. We don't have any heaters. So let's look at some different strategies, and we'll come back to that in a second. And I want to talk about telescopes that have glass in the front first. We're going to talk about SCTs. As I said, those are just such great examples. And Macs, of course, refractors. And then we'll come back and we'll look at glass in the back, Newtonians and open truss RCs and CDKs, and we'll see what works and what doesn't. And so let's start with SCTs. And I'm going to give you 5 strategies here. And on top of that, I'm going to grade them. The first one on the left is we wrap a heater strap around the tube of the SCT. I give that an F. And we'll talk about why in just a minute. We can also wrap the heater strap around the edge of the corrector. And I'm going to give that an F-. We can use a passive dew shield, which I've already talked about. I give that an A-, or we can heat the dew shield with some heater straps. I give that an A+. And somewhere between B and A, we can just attach fans to the front of this thing, and we just blow air over it and just don't use any heat at all. Well, let's look at these one by one. Why isn't heating the tube very good? Well, the heat has to conduct through the tube to the inner wall. And then the rear of the glass has to be heated by convection and radiation. And then heat has to conduct through the glass into the front surface. So yes, this works, but it requires a lot of heat. And all that heat can ultimately conduct into the optical path. So let's look at how much power do you need to heat from the rear? Well, this is the expression for conductive heat exchange. Again, it's the rate of heat exchange is just equal to this constant, the thermal conductivity constant, times, again, the area times the temperature difference and the amount of material that it has to conduct through. That's L. So a 5.4 millimeter C14 corrector requires 15.4 watts to maintain a 1 degree temperature gradient. So in order to counter that 3.5 degree drop that we talked about earlier, you need 54 watts of power that you need to pump into this thing. That's 5.4 amps for a 12 volt heater strap. And that assumes it's all going to go into the rear of the glass. It's 100% efficiency. It's not going to heat anything else up, which isn't really quite correct. But just that alone, that's 60 times more power than you need to just heat a dew shield. And I see this all the time. Guys do this. I see telescopes all the time with dew heaters on the tube. And it's just, it works. And I think because it works, people think, well, it's good enough. But it's not very good. I see this all the time too. This is really a terrible method. Just take the heater strap and wrap it around the edge of the corrector plate. Well, what's so bad about that? Well, first of all, remember that area quantity that I talked about in conductive heat exchange. The area along the edge of the glass is only 5.4 millimeters thick. Second, the glass is thermally isolated from the cell. There are centering screws that are nylon tipped, and there are cork spacers between the retaining ring and the glass. And all of those have very low coefficients of thermal conduction. So you're mostly heating the glass through radiative heating in the cell, And it's hard to pump enough power into this scheme to make it work well, even under mild conditions. And I've heard this repeatedly from people who do this. You end up with dew and frost around the center of the thing, and you've got your heater controller turned all the way up to max to even do that. So this is just a terrible way to do it. And I had to add this to talk about, how well does this work for retaining rings? Celestron sells these heated retaining rings. You can buy these things. I mean, the pros are it puts the heat closer where you need it. You need it at the front surface. Well, they were thinking and they said, let's put it at the front surface. The problem is it's a small contact area with poor thermal conductivity. Again, there's a cork spacer. There's a very large thickness of glass that you have to go through in order to get the heat to the middle of the corrector plate. So it works better for small scopes, but for C14, you've got 6 inches or 5.5 inches. I don't know the exact number, but you've got to conduct the heat all the way through there. So it needs to be really hot on the edges to just raise the center of that glass by 3.5 degrees. So this is really, I only give this a D+ at best with a dew shield. This I consider to be the ultimate dew protection, and I hate to toot my own horn, but this was my telescope down in Chile. It had an active heated dew shield, or not in Chile, in northern New Mexico, I'm sorry. It had an active heated dew shield that used radiative heating on the front surface. I then insulated that dew shield with reflectix to keep the dew shield to make the heat on the dew shield more uniform and to insulate it. So that I could minimize the amount of power I had to put into that to achieve that 3-degree temperature difference. I had a smart temperature dew point spread controller that controlled that 3 degrees. And then I insulated the tube with reflectix to slow radiative heat loss to the sky so that the tube itself wouldn't get super cold. And then I used Tempest fans to circulate ambient air in the temperature in the tube rather, to use convective heat exchange to try to better hold the inside components at the air temperature. That also prevents condensation on the primary, and it breaks up baffle plumes. And I also had a controller that only turned this on when there was a danger of dew. This did not run at all times. It only ran when the temperature dew point spread was down below, I think it was 4, maybe 5 degrees C. And then it would turn the system on. And I had that system down there for 5 years and I never once got dew. This worked just beautifully. And again, it minimized the amount of heat that was going into the system. How about refractors? This is a common heater placement that I see for refractors. Well, let's think about that one. Why isn't that any good? Again, the heat has to conduct through the tube wall. The heat has to convectively heat the inside air and radiatively heat the inside rear element. But here's the real killer. If you're using a high quality refractor, it's probably an Apple refractor that has a couple of air spaces in it. So it acts like a triple pane window. It has very, very low thermal conductivity to the outside surface. So you've got to crank up the heat as high as you can to get any heat to come through these heater straps to get to the front surface that really needs the heat. So you got to realize that when you put a heater on behind the objective, some of the heat's going to go through the glass, but the thing that's really doing the work here is the dew shield. The dew shield is really what's doing all the work, and those heaters are mostly just adding convective turbulence. And if you really want to add heat, the best way to do it is to add it to the dew shield. Just, bathe the front element in warming IR radiation. You only need 3 degrees C for a 1.5 aspect ratio dew shield, which is what's on most refractors. Really simple. There is one reason to heat the cell. Some refractors are not athermalized, and this came up on Astro maybe a couple months ago. And it was a brand new telescope, and as soon as the temperatures went down, diffraction-like spikes happened around all the stars. Well, this was happening because the cell wasn't designed well. And what was happening is it was contracting faster than the glass, and it was creating stress birefringence in the glass because there were 3 contact pads in there. And so it was putting a 3-point um, pattern, stress pattern, into the glass. And that's what causes this problem. This is not, strictly speaking, a dew problem. It's a thermal problem. The manufacturer ending up fixing it for this person. But that's another way to fix it would be to just gently heat that cell to hold it at a higher temperature. But again, you don't want that heat going into your optical path. If we kind of switch away from refractors and go to Newtonians, Newtonians are great. They have their own built-in dew shield. You know, the primary sits down at the back end of the tube. Fans work well to achieve faster temperature equalization. You may have to heat the secondary. The secondary is up closer to where it can get radiative heat exchange, and that may be necessary in wet conditions. But in general, all you need with a Newtonian is an appropriately placed fans, because the dew shield is so effective. I mean, the aspect ratio is huge. How about truss telescopes, RCs and CDKs? The plane wave scopes have heaters on the rear of the mirrors, and they also have fans. The goal there is to set the temperature for a very small differential to the ambient temperature, and only run them when they're needed. The plane wave controller runs them all the time, and I don't like that strategy. But if you can hold everything at the air temperature, that does work. You've got to be careful because the heaters are on the back of the mirrors, which are thick. So you've got a temperature drop. So you've got to figure out what's the minimum amount that you can run those heaters out. On the ASA telescopes, you have just fans, and they blow across the surface of the mirror. They break up the boundary layer, and they provide convective heat exchange that prevents dew. Some of these telescopes require the fans to run. My ASA telescope will not produce good imaging without the fans running. Other telescopes require that the fans be turned off. My old CDK required that the fans be turned off. And I believe that PlaneWave has had a couple of different configurations for the fans. So I'm not telling you what to do with your telescope. What I am telling you to do is experiment. You've got to check it to see which provides better imaging. In my view, the ideal anti-dew controller comes on and turns off within a specified temperature dew point spread. And you can control the heaters to a specific delta T relative to the air temperature for your dew shields. And I used to make these using Arduino controllers. But the good news is I complained to Celestron for years about this. And at one of the meetings, one of their guys came over and said, "Hey, you got to come see what we did. We listened to you." And I said, "What? Nobody listens to me." And they pulled me over to their booth, and they had introduced a new smart controller that does exactly what I told them was the best way to do it. So they now have a controller, and I have not tried it, but I recommend it. It measures the temperature, and it measures the humidity, and it calculates the temperature dew point spread, and it comes on at the appropriate time. So I give them big thumbs up. They produced a really good controller. I understand that the Pegasus DewMaster 2 is another smart controller that will do the same thing. You can plug in the appropriate sensors. There may be other ones out there that I'm not aware of, but these are the two that I am aware of. Or you can make your own. They're a lot of fun to make. And as we get to the end here, I've got one other big concern to talk about, and that is camera windows. Cooled sensors, we cool our sensors, that can pull the temperature of the window in front of the camera down below the ambient dew or frost point. And that can happen either inside or outside the camera, but I want to emphasize that something is seriously wrong if it happens inside your camera. The cooled cameras are constructed a little bit like I've shown here. You've got a sensor, and it's thermally in contact with a thermoelectric cooler, and that's all inside of a chamber. And that chamber is filled typically with dry gas. And there's a desiccant, and it depends on your camera. I've got one that's filled with dry argon. Some are just dry air. The really high-end scientific cameras that are cooled to minus 100 C, the old CCD sensors, they often had a vacuum chamber. Those were those are kind of, at least in the amateur community, those have pretty much disappeared. But excuse me, the whole goal of all of that is to either eliminate the dew point with a vacuum or to reduce the dew point so low that it's well below the cooling capacity of the thermoelectric cooler, so that you should never get dew inside. And if you do, you've got a problem. Outside the camera, convection, conduction, and radiation can cause heat flow from that warm outside air through the window to the cold sensor, which again is acting like a cold heat sink. And that window gets cold. And if the temperature of the outer window goes below the dew point, the dew is going to form, and frost will form if it's cold enough. And I think a lot of us know this, but a lot of us get caught by surprise. And so about 2 weeks ago, maybe 3 weeks ago, I can't remember, a couple of weeks ago, what could possibly go wrong? It was clear down in Chile. I happened to snag the temperature dew point plot from that night. The outside air temperature was about 14 degrees C, so a little cool, not too bad. The relative humidity was 38. That's not super wet. Dew point was near zero, so it's pretty dry. So let's start imaging. And I started imaging, and I got a phone call. And turns out the guy next to me in the observatory is Adam Block. And Adam has his telescope right next to mine. And Adam and I have spent some time working together on his telescope. And he and I talk a lot about the conditions. And Adam called me. And as you guys know, Adam's a very experienced guy. He knows what he's doing. And he sent me this picture. And he said, "What in the world is causing this?" And we both looked at this and scratched our heads. And it's, if you look at this carefully, you'll see it's kind of streaked and it's got some kind of fuzzy looking things on it. And we were scratching our heads, and both of us were kind of stumped. And I said, "Well, that's really strange." And Adam brought up the fact that there was a component he put in his filter wheel that he painted with some paint I recommended that's a little bit fragile. And he says, "I'm worried some paint has flecked off on this thing." And I said, "That's an interesting theory. Maybe they have to pull the camera off and clean it." And we kept talking, trying to figure out what in the world was this. And Adam mentioned he was pushing the camera pretty hard. And I said, "What do you mean pushing it hard?" He said, he's had it cooled to minus 20 C. And I said, "Oh, geez." I said, "You don't need to cool it that much." I said, "I want you to warm that thing up. That's too cold." Well, sure enough, I'll show you what happened. But what was going on is that camera cooled to 20 C, that sensor, these dark blotches were showing frost forming, and they were showing it on condensation nuclei that remained after the window had been cleaned. So what we were seeing was sort of a swipe from where the last cleaning action had taken place, and that was causing condensation nuclei. And so if you watch carefully here, this is where the sensor was at minus 20. And as Adam just turned up the temperature 5 degrees, look what happened. It all cleared up. So it turned out, I scratched my head over this and I said, "Well, let's confirm." I said, "That pretty much confirms that that's what was happening, but let's take a look at what went wrong." And I did a little calculation of that window temperature. And here it is. The red line, which you should pay attention to, is 15 degrees C ambient. And I calculated the temperature of that outer window for different cooling temperatures of the sensor across the bottom there. And at minus 20, look at that. That at 14 degrees C, that outer window was right around our 0 degrees dew point temperature. And remember, dew can form at about 3 degrees over that value. And I think what we were seeing, it didn't frost over. It wasn't completely frosted over. I think if you'd set that at minus 25, that entire window would have gone opaque. And it would have been maybe less of a mystery to us. I mean, we would have maybe seen something right away and realized, "Oh my gosh, that's frost." But the way that the frost formed, it was baffling to both of us. I mean, we both scratched our heads and said, "What in the world is this?" But so it's a lesson that, no matter how much experience you have, this kind of stuff can really catch you by surprise. And one of the things I want to emphasize with these, most modern CMOS sensors, they have very low dark noise, so they don't really require extreme cooling. The QHY 600M has, I think it's like 650 times less dark current than the old 16803 CCD. So, it's somewhere in the range of 500 to 1,000 times less dark current than the old CCD cameras. You don't have to cool these things, to minus 30 anymore. In most cases, minus 10 will work fine. And I've been operating with my cameras cooled to minus 10 down in Chile with great success for, a couple years now. And I've never seen frost. So it's something to consider. The main thing we want is we want the dark current noise to be less than the photon noise. And in general, that's not too hard to do with these CCD cameras. But, it's a good lesson to be wary when the relative humidity is over 30% and you've got a really cooled camera. So be really careful about that. Well, I always like to congratulate you guys. You sit through my technical, all this technical stuff. And, I really think that's fantastic that you want to learn more about this stuff. And now you have a better idea about how to protect your system from dew while hopefully minimizing or maximizing your image quality. So I can take some questions if you have some questions. I'll stop sharing my screen and we can hopefully, if you have some questions, answer it. So give me just a second here and we'll see if we can go back to a non-shared screen here.
Alec, you've been watching the questions.
Yeah, there are a lot of comments about people's experience with their own method of dew heating and or dew elimination and stuff like that. But there's one fellow that's asking a question that I would like to have answered too. You made a big deal about how the glass needs to be dew protected because it's pointing up to the sky, which is very cold. But where's Scott's first question? Wouldn't the air around the equipment also be radiating to the sky? And there are variations of that, including, isn't everything getting just that cold? So let's take it from there.
Yeah. No, that's a good question. Yes, and you may recall I mentioned that there's a type of fog called radiation fog. And radiation fog occurs when it's a dark, really clear sky. And the air itself can be cooled by radiation to be below the dew point. So the radiation is indeed affecting the temperature of the air. That's absolutely correct. But again, if it affects it to take the temperature of the air below the dew point, that's when you get fog. Mm-hmm. And that's when you get fog on a clear night. That's radiation fog. Under most circumstances, if the temperature, if the dew point is high enough, that amount of radiation isn't enough to pull the air down below the dew point. But it is enough to affect the temperature of the air. But again, if you can see the stars, the air is above the dew point.
Okay, I'm going to let Scott see if that answers his question, and he can respond down the chat down below. Yeah. Meanwhile, we'll turn over to John.
I think part of his question too is like if the ambient air is warmer than the sky, why isn't the corrector plate the temperature of the ambient air?
Okay. Yeah, that's a good question. So we tend, in our everyday experience, when we grab a coffee cup or we blow on hot liquids so we can drink them to cool them down, we tend to think those are really powerful effects. Those effects are linear, okay, with temperature. Those effects are working to try to hold the temperature of the glass at the air temperature. They are doing that. But at the same time, the radiative heat loss to the sky is pulling the temperature lower than the temperature of the air. And we don't really have good experience with how much power is being exchanged. And that's why I did that calculation to show, for the C14, that's 10 watts of energy is being radiated to the sky. That's a lot of power loss. And that's what's causing that temperature drop of the glass to go below the temperature of the air. And it's absolutely correct. Scott is right. That the air, by convective heat exchange and by conductive heat exchange is working to try to keep those glass components at the same temperature of the air, but it's not powerful enough to overcome the effect of the radiative transfer that is also working at the same time.
And does it have anything to do with the specific heat of the air being different than the glass? Like the glass is going to give up that heat more easily than the air?
That all relates to ultimately to the coefficient of heat exchange for those two processes. So the specific heat goes back to how much heat can be held and all of that stuff. That's kind of a different question. What you're really looking at is the rate of heat exchange. This is a heat exchange problem. And so we're trying to look at, in non-equilibrium here, how much heat is being injected by the air versus how much heat is being lost to the sky. And because of that T to the fourth condition, it's a pretty powerful mechanism. And I've noticed in my discussions with, folks online about this subject, that radiative heat loss, people tend to underestimate how powerful that is. And again, it seems crazy. It's cold out, and the sky, how could the sky have such a powerful influence on the temperature of my glass? But that is what's driving the temperature of the glass to be anywhere from, 3 to 5 degrees C below the temperature of the air. And by the way, if you go on your roof in the desert Southwest, when I was a college student, my friend and I went up with some binoculars to go look at the sky. We were in Scottsdale in Phoenix, a really hot area. And we were up there, and this in the winter times around Christmas, and we went up with some binoculars. We thought this would be great to go on the roof. And there was ice all over the roof. And my buddy said, where's this ice coming from? And at the time, I think I was a freshman. I hadn't studied much of this. And I left scratching my head going, where in the heck is this ice coming from? This makes no sense. Why is there ice out here? Now, it was a cool evening, but it was above freezing. And this was one of those cases where that radiative heat loss to the sky was enough to pull the temperature down to form frost on that rooftop. And it's a big effect that I think a lot of people who are trying to worry about don't kind of underappreciate. But those are good questions.
Scott has come back with, by sky, do you mean the air between, his question is, do you mean the air or space outside the Earth?
Well, it's both. So we talked about, when we're in space and we look up at the sky, this great blackness that's out there in the sky, that, excuse me, that blackness of space radiates at 2.7 degrees Kelvin, very, very cold. But when we're standing on the ground and looking up at the sky, we are looking through the atmosphere. And the atmosphere, it might be, the ambient air might, as I said, might be 5 degrees or 10 degrees. That's what we're talking about when we say ambient air when we're outside. But we're looking up at the sky through this column of atmosphere. And that atmosphere varies in temperature. It starts, it might be 5 or 10 degrees on the ground. I can tell you when I fly an airplane up at 40,000 feet, it's minus 50 degrees C. So the air temperature falls off as with altitude. It's called adiabatic cooling. If you're lifting a column of air through the atmosphere without adding any energy to it, it will cool off. And so that column of air, it's kind of complicated. Where you're standing on the surface, it might be only, say, 10 degrees. It was at 50 degrees Fahrenheit. But above you, if you were to go up 10,000 feet, it is considerably colder. And so these sky models that we talk about take into account, and that's why nobody calculates this. It's just too hard to calculate it. So they resorted to these measurement studies where they went out and they said, let's measure the temperature of the sky as a black body. And so, and that's a little complicated how they measure it, but just assume that they have a meter. They can point at the sky and say, what does this meter say for these conditions? And they measure it with respect to humidity, and they measure it with respect to temperature. And it's a big deal because they have to measure it over all these ranges to develop a model for the temperature of the sky. So when I'm talking about the sky for as far as we're imaging. I'm talking about standing out under the sky. Excuse me. And let's just imagine we're out in the desert where we don't have buildings and trees and all that stuff. It's a hemisphere of sky. And if we look up at the zenith, when we're talking about the temperature, that's what we're talking about, is looking up at the zenith. Now it does warm up as you go to lower angles and things. I mean, there's, I'm trying to spare you a lot of complexity here in terms of
John, if I take my telescope and point it straight up,
yeah,
it's pointing to an area that is, what'd you say, -10, something like that?
call it -20. -20 is a common.
Minus 20. Okay. What if I put a black painted piece of plywood right over the top 5 feet up in front of my telescope?
Yeah.
What's
So
it pointing to now?
yeah. So if you're pointed at that and that's at the temperature of the air, then you won't get radiative cooling. You've blocked it from the sky.
The radiation of the glass in the front of my tube
Yep.
is cooling straight through the warmer ambient air at the top of my scope,
That's right.
and it's cooling right through it and up to Orion.
That's right. That's right. It's the equivalent. I mean, let me really simplify it. It's the equivalent to take a great big piece of metal and make it really big so it subtends a huge angle in front of your telescope. And then take that piece of metal and cool it to -20 C and put it a foot above your telescope. That's what the sky is effectively doing. The sky makes it look as if there's a -20 degrees C, great big piece of metal there, and you hold that temperature right at 20 degrees C. That's what the sky's doing to you. And it's invisible. The radiation, it's not visible light. It's
No.
infrared radiation that's causing that cooling.
You are lucky we trust your expertise.
Well-
John, there was a question here about cooling the camera, cooling the sensor when it's a cold night, and I think you kind of addressed, how you should cool the CMOS.
Yeah. If it's a really cold night and it's really humid, you need to be careful about how you cool your camera. And by the way, this appears all the time on AstroBin. I see it. It's a regular occurrence. You wait until winter arrives here in the Northern Hemisphere. You're going to see post after post after post, because I know not everybody watches this channel. And folks go out and they crank their temperature down on a cold, humid night. And then they show up on AstroBin and say, how come I've got all these enormous halos around all these bright stars? Well, they frosted up their sensor. So, it's a very common thing to have this happen. And so, when it's really cold out, you got to be careful about how cold you're getting that front piece of glass. Because if it goes below the dew point or the frost point, it's going to frost up. You're going to have trouble.
So is -10? I cool mine to -10 C. Is that a safe?
That's what that's what I do too, Eric. I cool to -10, and for these cameras that works beautiful. The IMX 455 is pretty low dark noise. It's not 0, but 10 seems to work pretty well for my location. It may be low, maybe if you have a really humid cold night, you may need to go to -5 to avoid frost. But if you have frost, warm it up, warm up your sensor and try again.
But you're in the middle of the night and it's all remote, and so
it's remote. Yeah, no, you're in the same boat I am. If it happens, you don't find out about it until the next day.
Okay.
So on a
John?
related note, if you have a really hot cup of coffee, it's better to set it out and point it to the sky at night than blow on it. Is that?
Yeah. Well, yeah. If you have a nice hot cup of coffee, go outside and set it on a table and go mess with your scope for 5 minutes, and you'll come back and you'll discover it's not nearly as hot as it was. And that's part of it. Being exposed to the sky is certainly part of it. Now, if you blow on it, that's going to cool it as well. I think the radiative cooling there will be more effective actually than blowing on it.
John wants to know, keeping your optics free of dust will reduce condensation?
Not necessarily. So that's an interesting question. So the dust will provide what are called condensation nuclei. And that's what happened on the camera, Adam's camera sensor. There were little things adhered to the surface And it turns out that frost, and I don't ask me to completely explain this. This is just a fact. Frost tends to form wherever there's a little sharp point. Little tiny sharp points will attract frost growth. And those are called nuclei. And so if you have dust on your surface, I don't know that that'll cause condensation nuclei, but if you do get little particles adhered, what would happen to my scope a lot of times out in New Mexico is you get pollen that would come in during the right season, and it would adhere to the surface, and really microscopic pollen, and that can form condensation nuclei. So there is an argument to be made that, you know, having a clean surface is better than having a dirty surface with regard to frost and dew. But I would argue if you're doing it right, you shouldn't have that problem in the first place. If you use a dew shield or a heated dew shield, you shouldn't get frost. And by the way, I forgot to mention one thing. You know, I mentioned that strategy of taking an SCT and mounting fans around the top of it and having no heaters. So one of the guys at NEAC came up to me afterwards and he said, I'm going to build that. I really like that idea. And I said, well, I'm not aware of anybody who's done exactly that same thing. So let me know how it works. Well, I've been getting emails from him ever since then. And he built it. And he says it works like gangbusters. He doesn't ever get dew except for one night when fog occurred. Remember what I said, if fog occurs, all bets are off. You're going to get dew. And I said, in that case, you really want to have a little bit of gentle heat on that thing because that'll prevent dew when fog occurs. But he said he lives in an area where there's a lot of dew. And he said that whole scheme of just putting 4 little fans around the front of it. And he went to a lot of trouble. He sent me pictures of it, the whole thing. And I meant to mention that because I hadn't seen that done before. It's done on my telescope, on my 24-inch telescope, but I'd never seen that done on an SCT. And he says it works really well. So
John,
that's another way to do it. Yeah.
Yeah. IP's got a question, but before I ask that one, I want to ask one for myself. You said when you point your scope up, the temperature's minus 20 degrees, whatever it is. That's at night. What is it during the day?
Well, I don't have any data on what it is during the day, but the daytime temperature, sky temperature is considerably warmer. It's not minus 20. I don't know what it is during the day, but remember this, during the day, you can see the sky, right? What color is it? It's blue, right? Well, that automatically says, and what do blue temperatures imply about the black body radiation? That implies automatically a much warmer temperature.
Okay. What about the atmosphere? What is it about the atmosphere that keeps the sky temperature as measured from the ground from reaching the temperature of the CMB, cosmic microwave background, I guess?
Well, yeah. You know, I think that's been a question for a long time. You know, we get solar heating during the day that heats everything up. We've got heat radiating back into the atmosphere all the time. It has a certain heat capacity where it can hold heat. If you were to turn off the sun, you would discover very quickly that the Earth would cool, the atmosphere would cool. Everything, it wouldn't take very long at all for the atmosphere to get a lot colder than it is. So it's solar heating during the daytime that's heating up everything on the surface, and that in turn heats up the atmosphere. It causes all the convection, it causes all the weather, and it's the heat capacity of the air, of that huge volume of air. And by the way, you know, one of the remarkable facts that I love to relate when I'm talking about aviation stuff, and I think it's relevant here, is just how much air there is. You know, we tend to think about air as being this sort of lightweight thing. And, you know, we don't think about how much there is when we talk about heat capacity. But, you know, a thunderstorm, which has a lot of water in it, one big thunderstorm can weigh millions and millions of tons. Okay, almost 1 billion tons for really large ones. We don't really think about how much mass is involved when we're talking about the atmosphere. And it's a lot of mass. And by the way, which is heavier, humid air or dry air?
Well, any chemist will tell you that H2O weighs less than.
There you go. You're Eric, you have the right background. to answer
I,
that.
I cheated when Susie said that. Yeah, that's 18 versus 28. So
No, that's right.
Yeah.
So, but a lot of people, you'd be surprised. And I love to do this as a survey, and it's usually 50-50. So if you haven't thought about this, and I say all the aviation guys have to learn this, and the chemists, of course, have to learn this. But for people who haven't really thought about it, you think, well, water's heavier than air, so it's got to be heavier. Right?
not water vapor.
But not water vapor. Water vapor is a lot lighter than nitrogen and oxygen. So it turns out when we talk about those thunderstorms weighing hundreds of millions of tons, that's a big column of very, very light air. So, when we talk about the heat capacity of the atmosphere, it's really quite large.
If you have a truss telescope, should you be wrapping it with a shield around them or leave it open?
Well, excuse me.
Excluding the issue of stray light or dust or all that.
Yeah. That's a good question. ASA has obsoleted my version of the ASA 600, and they've come out with a solid tube 600. Now they got rid of the open truss, and they did it for some other reasons. But a couple people have said to me, is that a better way to do it? It's it cuts out stray light, and you can make it more dew resistant, and that's all true. I guess it just depends on what problems you have with dew. I mean, the biggest problems I ever had was in northern New Mexico with my SCT. That is a very, very wet location. And it's wet in the wintertime. You get frost shutting things down. It's wet in the summertime with monsoons. And dew and frost are a huge problem out there. And so I had to really focus on how do you really solve that problem. Now, if I had an open truss system out there, I might be looking at trying to wrap it up in reflectics or something, because that could be more of a problem. So I don't really know the answer to that. It probably depends on where you have it and how serious the problem is.
John, we've got a couple of more questions.
Sure.
Go ahead.
We have a couple more questions from IP. Is the reason that fog and dew can begin to form within 3 degrees of the dew point because the temperature within an air mass can vary by 3 degrees?
Well, it's both the temperature and the humidity can vary. It's not a uniform process. I mean, as the air moves around, and so the general kind of common wisdom, and this originally comes from my pilot experience. If you're flying an airplane, the common wisdom, and I teach students, if you're within 3 degrees C, the chance of the airport going under a layer of fog where you can't get back in is pretty high. And I've noticed that even when I'm using my telescopes, that 3 degrees is kind of a fuzzy area where, at the top of that 3 degrees, you can start to get a little bit of dew, a little bit of frost. When you hit the full on dew point, that's when you're getting a lot of water coming out.
And is the SCT fan design that you described, is that available online?
I'm sorry. Say that again. Which design?
Yeah, you described a fan design for removing dew from from a Schmidt-Cass.
No.
Is the design available?
No, it's not. No, I just pointed that out because that is a valid way to counter dew using convective heat exchange. And excuse me.
Okay.
So that is not something that is commercially available. And the one guy that latched onto that idea at NEAC went out and built his own, and he made his own, and it worked. He tells me it works really well. So and he didn't make it really. He made it maybe an aspect ratio of 1/2 or so. So it's not a super deep design. And he put 4 fans on it, and just out of memory, I mean, they weren't super small, but they were maybe 1.5 to 2 inch fans, and he used 4 of them. And I don't know how he arranged it in terms of airflow, whether some were flowing in and some were flowing out. I think that's the way he did it, but I'm not 100% sure.
Thank you. And I believe we've got all the questions, Molly, Eric.
Yep. All
Good.
righty.
Well, all good questions.
Yeah, that's a lot of great discussion, a lot of great physics, and a lot of great knowledge. People can go spread the good word.
Hopefully, a few less food fights online. That's what I want to see.
potentially. Yeah, I might go chop up parts of this video so that people can reference it more easily in the forums and stuff like that.
Sure.
Yeah, so if that is everything, then again, if you are interested in, sorry, my cat's trying to get my attention. If you're interested in coming on and giving a talk, say like on some basic topics of astrophotography for beginners, or if you want to make the talk about a survey of target finding tools, please hit the contact us button on the astroimagingchannel.org on our website, and one of us will get back to you. And I think with that, we will call it a night. So good night, everybody.
Good night.
Thanks, Jaime. Thanks, Jaime.
Have a good night.
Thanks for
Thank
coming
you
on
so
again,
much,
John.
Jaime.
Thank you.